Good afternoon. I'm sorry I'm not here to give you this in person, but today we're going to go over some of Newton's second law and its applications. As you watch this video, I would really recommend pulling out the PDF of the notes and trying to work through and follow directions. Maybe you could have one person in your group work on this. You could get a separate piece of paper. You could put this in the corner of your screen so that you can work. And if you have any questions, please be ready to ask them on Thursday. We'll do a lab, but we'll have lots of time to get your questions answered. But we're going to dive into Newton's second law. So just a reminder of what we talked about last class is we reviewed Newton's 3 laws of motion. And the first law is known as the law of inertia. It says an object in motion stays in motion, or an object at rest stays at rest unless there's an outside force. We call this the law of inertia. The second law is the one we're going to focus on today. Sometimes people know it as the equation one. It says that the net force is equal to mass times acceleration. And the third law says for every action, there's an equal and opposite reaction. So like I said, today we're going to focus on the second law that says F net equals ma. One of the ways that we understand what the net force is, what exactly is a net force? We do that by using something called a free body diagram, or sometimes we call it a force diagram. In a free body diagram, we represent whatever object we're talking about with either a box or a dot. And we draw forces that are acting on that object as they're coming out of the box or the dot, whichever one. They always push out. And the direction shows us which direction the force is acting. And we're going to label each force. So like a really common downward force would be the force of gravity. Maybe you'd call it Fg. And the longer that you draw the arrow, the more magnitude that force is. Remember, magnitude is a word for value. So a longer arrow would mean that there's a stronger force. A shorter arrow would mean that there's a weaker force. Okay, I'm going to have you take a second with this one. I would suggest pausing the video and trying, looking at these free body diagrams. Which direction would each box accelerate? Okay, hopefully you've paused it and tried it. This on box A, I would say the up and down forces look balanced. The left and right forces look balanced. There's 0 acceleration. Same thing on B. There's no side-to-side forces. The up and down forces look pretty darn equal to me. It would not accelerate. Box C would accelerate to the right. Box D would accelerate to the left. And E, the up and down forces look balanced, but in terms of the left and right ones, that left force looks stronger. So it would feel an acceleration towards the left. Okay, now we're going to combine skills. We're going to use what we talked about last week with our new concept of which way would it accelerate. So these are 3 velocity time graphs, and we're trying to match the velocity time graph to the correct free body diagram. I'm going to pause and hope you try this on your own. Hopefully you're unpausing me. This first velocity graph, it shows a motion at a constant negative speed. The key word in that, though, is the speed isn't changing. No changing speed means no acceleration. The free body diagram that shows no acceleration is the third one, where all the forces are balanced. The middle free body diagram shows a velocity that's always increasing, or it's becoming more and more positive. Positive is to the right. The first free body diagram matches that one. The third velocity graph is always decreasing. It's accelerating towards the left in the negative direction. So there's how that one matches. Okay, another one to try on your own. What is the net force on the object below, and which direction would it accelerate? Okay, when I'm looking at this one, I say there's a force of 10 newtons to the left and 8 newtons to the right. That means I have 8 newtons in the positive direction, 10 newtons in the negative direction. Sometimes it helps students to think helping forces minus hurting forces. So 8 newtons minus 10 newtons is negative 2 newtons. So the net force is negative 2 newtons. And because it's negative, it would accelerate to the left. To calculate net force, you're going to consider all of the forces that are pointing on the right, and we're going to call those positive. And we're going to call every force that's going to the left negative. And we're going to do very similar if there's up and down forces. We're going to call up positive and down negative. We're going to sum our forces. We're going to add up everything that's going in the positive direction and subtract everything that's going in the negative direction. And again, a tip that helps some students is think helping forces minus hurting forces. So let's practice some of these on the next slides. Okay, I'm going to talk slowly to give you time to pause me. What is the net force on the objects below? Which direction would the objects accelerate? Okay, this first one, I have a total of 10 and 5. I have 15 newtons to the left. I have 16 newtons to the right. The net force is going to be 16 minus 15, which is 1 newton, and it's going to accelerate in the direction where there's more force, to the right. On this one, I have 7 and 9. I have 16 newtons to the left. 8 and 8 also is 16 newtons to the right. This one has a net force of 0 newtons, which means 0 acceleration. No force, no acceleration. If you get a net force, it means there's no acceleration, and the term we use for this is equilibrium. What that means, sometimes students think that means that the object is stopped. That's not what it means. We got to think back to the first law. An object in motion will stay in motion. An object at rest will stay at rest. So if it was at rest, it won't move. But if it was moving, it's going to keep moving in a straight line at a constant velocity. If there is a net force, the object will accelerate in the direction of that net force. So the object will be increasing in speed as long as that force is applied. This is Newton's second law, and this is our famous physics equation, F net equals ma. So here's our famous equation, F net equals ma. It's a way that helps us connect the ideas of forces and motion. This is an equation we're going to use for the rest of this unit. So let's practice using the second law. Here's a force diagram. If the box has a mass of 2 kilograms, what will be the acceleration of the box? Okay, first thing I notice is that the vertical forces are both 18 newtons. They'll cancel. I have a rightward force of 15 newtons and a leftward force of 7 newtons. So my net force is going to be in the horizontal direction, and I'm going to get 15 newtons minus 7 newtons. My net force is 8 newtons. To turn that net force into an acceleration, I'm going to use my equation. F net equals ma. The net force is 8 newtons. Oh, I'm going to drop units. Sorry. The net force is 8. My mass is 2. And I'm going to find acceleration. Acceleration is going to be 8 divided by 2, which is 4. And the units for acceleration are meters per second squared. I should have highlighted that on the last slide. The unit for force is a Newton. Isaac Newton is our guy who made force. The unit for mass is a kilogram. And the unit for acceleration is a meter per second squared. Okay, here's another one. A 2-kilogram box is being pushed along a table with an unknown positive force of 10 newtons of force being applied in the opposite direction. If the box has an acceleration of 5 meters per second squared, what is the unknown force? Okay, so on this one, I'm going to assume that the force of the box and the force of the table cancel each other. But the net force is made up of the difference between the applied force minus that backwards 10 Newton force. My problem here is I don't know what the net force is. I don't need to get stressed. I can use the equation F net equals ma. I was told that the box weighs 2 kilograms and it has an acceleration of 5 meters per second squared. 2 times 5 is 10 newtons. And now I can plug that in to my formula. 10 newtons is going to equal the applied force minus 10 newtons. A common wrong answer is, oh, my applied force is 0. Not quite because of that negative. I'm going to add 10 newtons to both sides. 10 plus 10 is 20 newtons is what my applied force is going to be equal to. Something that we're going to account for sometimes is weight. Weight is also known as the force of gravity. We talked about last class that the force of gravity is mass times gravity, where gravity is always the same number, 9.8 meters per second squared. That's gravity on Earth. We are going to assume, unless you were explicitly told, that we are solving these problems on Earth. So this says a 2 kilogram box is being pulled upward by a string with 25 newtons of tension. What is the acceleration of the box? This is one, if I was here, and we'll do it together in our lab on Thursday, I would demonstrate this. The box has a downward force of gravity, or the weight, and there's an upward force of tension, and we're going to just let the box hang from a string. So there's my free body diagram. I am trying to find the acceleration of the box. So my net force, I'm going to do, instead of right minus left, I'm going to do up minus down. So it's going to be my force of tension minus the force of gravity. The force of tension, I was told, it's 25 newtons. The force of gravity is mass times 9.8. So my net force is 25. 2 times 9.8 is 19.6. So I'm going to take 25 minus 19.6, and I got a net force of 5.4 newtons. To turn that net force into an acceleration, I can use F net equals ma. 5.4 equals 2 times a. My acceleration is 2.7 meters per second squared. Okay, next example. A 2 kilogram box is being lowered by a string with 15 newtons of tension force. What is the acceleration of the box? Okay, so this one now, if I draw my free body diagram, I'm going to draw my force of gravity down and my tension up. That doesn't change at all. But now to find my net force, it still is going to be the upward force of tension minus the downward force of gravity. My tension is 15 newtons. My force of gravity is mass times 9.8. 15 minus 19.6 is negative 4.6 newtons. So because it had that keyword lowered, my net force is negative. Once again, to turn that into an acceleration, F net equals ma. Negative 4.6 equals 2 times acceleration. My acceleration is going to be negative 4.6 divided by 2, which is negative 2.3 meters per second squared. Last one, and you guys have done it. A 2 kilogram box is being lowered by a string with an acceleration of negative 1 meters per second squared. What is the tension in the string? My free body diagram still hasn't changed. There's still a force of gravity down. There's still a force of tension up. To find, now what I would do first is find the net force. F net equals ma. My net force is equal to 2 kilograms times negative 1 meter per second squared. It's negative 2 newtons. Now let's go back. We know that the net force is equal to tension minus gravity. Well, my net force is negative 2. Tension is what I'm solving for. The force of gravity, it's that 2 times 9.8, which is 19.6. The force of tension is 19.6 minus 2, which is going to be negative, oh, why did I get it? Nope, it's going to be positive. Sorry, I was trying to math in my head. Positive 17.6 newtons. Okay, you guys did great at following along. I hope that you got through this and that you come to class Thursday with any questions you have, but now you should be ready to try your class kick slides for the day. See you on Thursday.